Allez, on attaque. In English, so. So, thanks a lot to the Links organization for the invitation. It's a pleasure to be here. So I think I gave a talk, but like 10, 15 years ago at Links in Place d'Italie, and then I have kind of a black hole when working for Huawei. We are not so much welcome in this environment. So I'm glad to reconnect with you, and I'd like to talk about a topic that is exciting me quite a lot, that being, which is network acceleration for AI. And so it's activity where Nokia will be more and more present. So we are quite strong in optical modules that are being sold to hyperscalers, so for the interconnection of compute and data centers. And one of the future items will be to do more on the networking side. So historically, it was more cloud computing. And now we are shifting towards network for AI workloads, so AI clusters. And it's a lot about GPU networking. So just one slide on me. So I started my career at Thales, working on mobile systems, on mobile communication. Then towards the end, I transitioned to SDN, mostly on mission critical overlays. And then I joined Huawei, where my work has been very much on the design of control plane algorithms for the SDN controllers. So working on the routing problems, load balancing problems, resource allocation, and so on. So before I left, I started to work on network for AI, so network acceleration for AI. And I'm now happy to have the opportunity to continue at Nokia on this topic. But I have a team with also a little bit broader topics, so on AI for network, so management, application of AI for the management of network and network automation, and network acceleration for AI. So it's not the only topic. So this presentation is articulated in two parts. The first part, I'll share some background on AI data centers, sharing information about the scale of operations, the nature of the workload and the traffic, both for training and inference, and some elements about the compute and network stack, so the technology that you find in a data center. And in the next part of the presentation, I will highlight research topics that are super active at the moment on load balancing, collective communication, transport and congestion control, and also reconfigurable topologies. So yeah, the challenge is for training, at least, is to be able to train very large models. So in particular, large language models, where a single GPU is not enough. So it means that either the data don't fit inside one GPU, and then you have so much parameters in the model that also the model doesn't fit in the GPU. So just to give a few numbers here, you have the largest Llama 4 model, which is 2 trillion parameters. And it's trained also on input data, so number of tokens, which are trillions of tokens. So you need really a super computer. So in principle, you could think it's kind of easy. You buy a lot of GPUs, which are expensive, by the way, and you connect them with the network devices, and that's it. But it's much more complicated, as you can guess. So to do that, you have to rely on different type of parallelisms to accommodate either the data or the model parameters. So if you would have small data and a small model, you would put everything on the GPU. If you start to have large data, you have to split your data and operate in parallel over GPUs and then aggregate gradients and so on. So this is called data parallelism. If the model starts to be too large, you have two basic solutions, two initial solutions. There is actually a lot more type of parallelisms. Here is just the most popular ones. There is one called pipeline parallelism, where the layers of the model are processed by different GPUs. So you have here model 1 entry layer is processed by the GPU, and then when the operation is done, you pass the data to another GPU. At the same time, so when the calculations are too complicated, so the matricial operations are too large, and it cannot be handled by one GPU. You have to split the calculations over multiple GPUs. And so when you do matrix multiplication, but you can work with algebraic operations to decompose them and to be able to operate on multiple GPUs. So that is called tensor parallelism. And so that's when the matrix is too big. In reality, so when you train a very large model, the several type of parallelisms are combined. So we are talking about 3D parallelism, 4D, 5D, and so on. So you have an example here where at the same time in the data center, you have some GPUs that are exchanging data with data parallelism, but they can be also nested in a loop using pipeline parallelism and so on. So what does it mean in terms of traffic? You can see here a small drawing on the top right here of the figure, where you have steps, very big steps that are part of a pipeline. And inside each step, at the beginning, you need to spread the data over the GPU. So this is data parallelism. And once the data are distributed to GPU, you have a lot of subsequent operations which can be handled by tensor parallelism. And what does it mean in terms of communication between the GPU? Actually, there is a mapping for each type of parallelism to what is called a collective. And a collective, for those who have studied parallel distributed computing or parallel computing, you all know MPI, where you have primitives and in AI data centers, a subset of these primitives, not all MPI primitives are used, and in particular, all reduce, all gather, all scatter, broadcast, etc. So you have 4, 5 high-level primitives that are typically used to handle this type of parallelism. And here you can see a table. So in general, data parallelism is implemented with all reduce, and a pipeline parallelism is implemented with point-to-point communications. So just to give 2 examples. And you can see a small example on the figure. So when you have some data that you want to distribute to a GPU, so you are here you have one collective that is passing the data. The GPU are making their computation, but then when you need to aggregate the gradients and do a small numerical operation like an average or maximum, you can use all reduce primitive or collective to gather the data and calculate the output. That's for training in general, but it's also, you find also the same for inference. Inference is a little bit, one particularity of this is that it could also be distributed. And there is a popular scheme called prefill and decode in particular. So prefill is the embedding of a prompt into the space of the LLM and the generation of the first token. After you do that, so this step can be parallelized over multiple GPUs so that what you can see on the picture. And once you do that, what is extracted from the model, it's the model parameters that are specific to the prompt that have been embedded. And it's formulated as a KV, so-called KV cache, so key value of parameters related to the model. And that can be transferred to a subsequent set of GPUs that will do the token generation. And so that's the decode phase. And there are nice papers here showing that the 2 operations, the prefill and the decode, are totally different in terms of computation, and you don't have interest to mix them on the same machine. So if you want to keep the GPUs busy, you have better interest to disaggregate the inference part, and you can multiplex multiple prefill and multiple decode on the same pool of GPU so that they are kept busy, 100% busy. So that's in general the target because it's very costly infrastructure. So you want to really maximize the utilization of the resources that you have. So what does it mean in terms of network? Is that between the prefill and decode, in general, you have the KV cache transfer. So it's a large amount of data. It can be several gig, even for one prompt, between 2 pools of GPUs. And you have to do it super fast because we have KPIs here, which is time to generate the first token or time to generate the subsequent tokens. So the collective I was mentioning here, you have small examples for the most popular ones. So all gather, all reduce, reduce scatter, all to all broadcast. Just to highlight one, so I'm pretty sure you've seen that before. So all reduce is that you have chunks of data, tensors that are available at different GPUs, identified by their rank. So in the HPC world, it's the ID of the GPU, and they are different. And what you want is to aggregate them and calculate a numerical. You want to calculate the average or the maximum on the tensors. So at the output of this operation, you should find on the same pool of GPU the same output tensor, which is the average or the sum of all the input tensors. Okay. So this is the primitive, let's say. What I showed you is what do you have as input and what do you have as output. But I didn't tell you how do you schedule the transfer between the GPUs so as to implement this type of primitive. And so that's what is called a collective algorithm. And there are many algorithms compiled into libraries. So we are talking about collective communication libraries. And the most popular one is the one from NVIDIA. It's called Nickel or NVIDIA CCL, but there are many others, Microsoft CCL, Huawei CCL at the time, etc. So the challenge is to find the best algorithm that is scheduling the transfer of chunks between the GPUs so that the completion of this collective is the fastest as possible. So historically the network was not a bottleneck in HPC. And so people have not invested a lot. And also the topologies that were inside the clusters, the computing clusters, they were super homogeneous. So it means that in general, you had only two hops between a machine and the delay was bounded. Plus infinite capacity, so that it was a so-called non-blocking fabric inside, so you don't have a bottleneck in the middle. So the algorithm that is implemented in all computing clusters or MPI, the most basic one is called a ring. And ring, it's like you have a tensor at every GPU, so it's called a processor, it's a GPU. It's split into chunks. And at each step of the algorithm, you pass a chunk to the GPU that has a ID plus one. Very basic. And actually, this algorithm is so-called bandwidth optimal when the topology is symmetric, so it has a bounded delay, and there is no contention. But it's not delay optimal. So if you want to improve a little bit the delay, what you can do is that you can create trees and trees that overlap. So you can see here the same set of GPU. This one is the root node of one tree. But at the same time, this GPU, which is a leaf in the first tree, is also a root in the other tree. And you could run the two trees in parallel so as to minimize the delay for the completion of the algorithm. It's just two very basic examples of what has been done in the HPC world. Now in AI clusters, people don't use this anymore. I'll show you. Let's move now to the compute stack. So you have to understand what is inside the data center. I show you here the Huawei one because we always see the NVIDIA one. So what you have you have an AI stack. So you have like a PyTorch library that you use to implement your model, and at the end you have backends so that the model is executed over GPUs. So in the NVIDIA world, it's the CUDA backends. In the Huawei world, it's called CAN. So they have their own CUDA model running on top of their GPU or NPU cards, which is the Ascend card here. So that's for the machine learning stack and how you do the calculations. But at the same time, you have a cluster with a lot of machine. So you also have this stack here, which is managing the compute resources and distributing the workloads around the cluster. And so in particular, in this stack of software to manage the cluster, you have a scheduler. So here, Volcano scheduler is it's a job scheduler in the AI cluster, which is connected to the HCCL. So it's a collective communication library scheduler. And so this guy is a centralized master that will create so-called backend. Uh, so that pools of GPUs, so set of GPUs, will be able to execute all reduce, all gather. So each primitive is configured by a centralized controller, and it's orchestrated by the cluster manager. Then after, when the chunks are exchanged between the GPUs, the controller is not anymore involved. It's totally distributed execution. You could do something hybrid, but it's in general, it doesn't scale, so people want to have distributed execution. So I show you the machine learning part, the cluster part. And now, what is the network? So the network inside the data center, you have a front end in general, so it's classical cloud network to network here based on Ethernet, so that the users can connect from the outside to the machine. But the interesting part is what is called here scale up and scale out. So scale up is a very local, high-speed network so that the GPUs can exchange data directly. So in the NVIDIA world, it's called NVLink. It's a proprietary technology, but there are now consortiums. I put the name here, Ultra Accelerated Link, which are aiming at providing a standard for this type of networking. It's multiple terabytes per second of data, and it's very short range. So it's everything is happening inside one rack. So it's within the rack. And you have the scale out, so it's between the rack. So when you want to interconnect GPUs from two different racks, it's also Ethernet based. It was RDMA, so I'm sure you heard about this. So remote direct memory access. Which was originally proprietary. NVIDIA has acquired Mellanox, etc. And now there is also a consortium that has released the first standard called Ultra Ethernet for the scale-out part. And so in terms of bandwidth, we are at 800 or now 1.6 terabytes per second between two GPUs that are not in the same rack. So the scale-out part comes from InfiniBand, as I mentioned. Just here you have this small drawing where the goal of these protocols for the scale-up and scale-out is to bypass the host. So you can see that the CPU and the host side is not involved, and you do memory-to-memory copy. So you can copy a tensor from one GPU to another one without involving the host. And it's a smart NIC, so it's accelerated inside the hardware to handle all the transport layers, so congestion control, flow control, etc. So originally it was InfiniBand. Everything was proprietary, so they were defining everything from the transport layer to the physical layer. And then after there was a shift towards Ethernet-based technology. So the first version called RDMA over Converged Internet version 1 was over Ethernet. And then it went over UDP with the version 2. And some extensions have been also developed for long distance. It's called iWarp here. So I put you the little history here with the standardization. You see it has started in 2010, something like that with V1 and V2. And then people were trying to modify, improve congestion control. And so there are very popular schemes, in particular timely, HPCC, and DCQCN, which are improvement of the congestion control for inside the data center. Well, as the data center size has grew, and there was a need to interconnect data centers, the need for what is called scale across has come. So initially it came from the research part. So you have good papers. You could particular Bifrost from 2023. So you can see that it's quite recent. And the need was that, okay, you don't have enough energy locally to accommodate the need inside one data center. So maybe you need to distribute a little bit to leverage compute that is distributed. And so if you want to do that, you need to transfer data between GPUs uh, located in different DCs. And now the new thing is to redesign completely the transport layer. I'll come to that with this Ultra Ethernet consortium in particular. You see, in terms of market, most of the market today is still based on InfiniBand, but the Ethernet is ramping up quite quickly. So the future is Ethernet. So what did this UEC, so Ultra Ethernet Consortium did? They kind of reinvented the transport layer. One of the key contribution was to have uh, um, multi-pass. So be able to spread the traffic over multiple paths. And so if you want to do that, so because you have small delays on the different paths, you may have some misordering of the packets. And the original standards like RDMA were not adapted to that because they have not been designed by networking people. At the HPC times, networking was not a bottleneck. So the very basic transport layer mechanism was go backend. If you lose a packet, you just restart from what you have lost. And so there was no selective acknowledgements, and something called PFC. PFC is priority flow control, which is a kind of back pressure mechanism. So you have a switch that say, okay, my queue is too big, so please upstream a device, stop sending traffic. So it was kind of pause, stop and go process at the link layer, which was really bad for the transport or the end-to-end layer. So yeah, they were at that time they were talking about lossless fabric because if you, I mean, every time your buffer is starting to go above a threshold, you stop sending, then you never have a congestion, but at the same time you are totally inefficient. And so the challenge was to, let's say, restart with the lossy fabric where you can actually have, in theory, you can have losses inside the network. But you design your transport layer so that it really becomes lossless, so that you don't have losses. So they design multiple congestion control algorithms. So one is sender-based, yeah, which is the mandatory one based on the RTT and the ECM. So they are, at the moment, it's just version 1, but they are rethinking these signals, congestion signals, so as to improve the transport layer. And another one, which is receiver-based, based on the credits. That is sometimes useful. So when you have a GPU that is too busy to digest the data, you can slow down the input stream. So you can tune the transfer based on the GPU load. And trimming, also trimming is the fact that if the packets that are sent are large, but if you have a congestion, even if you don't want to lose totally the packet. So you take the part that fits in the buffer, and you can dynamically split a packet and send a negative ACK to the source saying that, okay, I splitted your packet, part of it has been lost, so you know. That's called trimming. So there are active active projects in this consortium. So one is on this lossless mode. So it's retrocompatibility with the PFC, so the old style transport from HPC. One is called programmable congestion management. So that can be useful because if you are inside the data center, you have very small buffers, so a few kilobytes. So in principle, you have to control the rate based on the ECM, so explicit congestion signals, so that you don't fill up the buffers. But if you are more on the long range, the delay are longer, but also the buffers. So in this case, the RTT is the key indicator. So you want to keep RTT low, and um, it will avoid congestions. And so if you have a programmable congestion management, but you can navigate between those two mechanisms, and you can switch from one mode to another mode. Congestion signaling, it's the cooperation between the smart NIC and the switch. So I told you about ECN, so we know this mechanism for a long time, but now we have a lot of telemetry inside the switches, and we can extract much more KPIs so that the smart NICs know a lot more about what is happening inside the fabric. And last topic is the convergence with the scale-up. So there is a war at the moment between scale-up and scale-out. And the scale-out, so Ultra Ethernet, so between the rack, are trying also to provide a solution for inside the rack. And the consortium that is working inside the rack is also trying to expand outside the rack. So, okay, we are talking about scale-up and scale-out convergence. So that's the last slide on the background, and then I move to the research topic. Just here, this table, you can show see the difference between what is happening inside a cloud computing or a regular data center versus AI cluster. And what you have to remember is that it's mostly, so it's GPU to GPU communication of a set of flows that are synchronized because of the collective layer I showed you before. So when you start all reduced communication, you have at the same time a set of GPUs that is starting to communicate at the same time. And when they start to communicate, it's not small flows, it's elephant flows. It means that it can saturate the NIC interface. So you can have a 200 gig flow starting between two GPUs. So that's huge. And so because the flows are huge, it means that you cannot resort to ECMP, for instance. If you do hashing for the load balancing, but you will have collisions. So let's talk to load balancing indeed and move to the research topic. So here I showed you before, so the target, the initial picture of the cluster was to build a data center with 100K GPUs, huge. And the question here is how can you do that with the hardware that we have today? So today we have switches here that are in general 64 ports of 800 gigabits. So if you have a 2-tier or 3-tier topology like you have here, actually you can calculate that the maximum number of GPUs that you can accommodate, if they all saturate the interface when they communicate, is 64K. So to scale up to 100K GPUs, you have two choices. So either you expand with another layer, so you can go 4-tier topology, or you pull more GPUs to the input port, but it means that you will have congestions. But actually, you have congestion in the two cases. So even if you expand this topology to 4-tier layer, at a given point of time, if all the GPUs are sending traffic to a rack, you will have incast congestion, so-called incast congestions. So it means that you have to sort out congestion inside the data center. And we saw before that the Rocky, at least the older version of the transport, like RDMA, etc., they don't like reordering, packet loss, etc. So they are super sensitive to that. So one topic is load balancing. So when you have, what you want is that you totally eliminate congestion, so before it happens. So what can the switch help? So if you are here at the bottom switch, and you have GPUs that are sending up some traffic, but you can observe the link loads, and you can make some selection. But at the same time, you can see that once you have gone to the spine and then you go to the destination leaf, but you don't have information about the congestion of these links. So you will create congestion. There are many ways to deal with congestion. At the moment, there is no big consensus, but people have to see if they want the host or the smart NIC to be active at the load balancing, or if it is the switch. So you have two types of solutions. For the host side, you remember classical load balancing in networks is ECMP. So what you can do, ECMP is based on a hash on the packet header. So what you can do is that you can play with the entropy parameter. And if you change one field in the header of packets, it will change the path decided by the hash. Once you have done this decision, you can observe the congestion. And so over time, you can maintain a list called a bitmap here in one approach of the paths that are good for you. So the least congested path, for instance. So that's one approach that is mentioned here. And on the other side, the switch side, we have other technologies on the switch side here, which are inside the data center, you have a routing protocol, generally BGP based, and you have many parallel paths because you have between two leaves, you can have a rebound again over a spine, different spines, so that you have hundreds of parallel paths in the data center. And so BGP is establishing this path. And so some extensions to BGP that have been proposed is the possibility to advertise and select a set of paths to the host. So you have the switch here, the edge switch is making an inventory of the path and collecting monitoring information so as to expose a subset of paths to the smart NICs. So that's another way. You also have a centralized approach. It doesn't scale, but some people are using this in particular setups. It's called flow scheduling or deterministic routing. So you can select from with a centralized controller a particular path for each flow. And the alternative is packet spraying, I was mentioning before. So you have load balancing, you have two ways in general, flow-based and packet-based. The packet spray is the per packet load balancing. So it's this one. So the leaf here, the source leaf is spreading each packet to a particular path. And so here you can see a benefit. So you can, in terms of completion time, you can really accelerate the completion time of flow completion. And here they compare the spraying of packets versus the routing over a single path. So you can have good gains, but at the same time, these paths in general, they have ultra short latency, and the buffers are also very small. So it means that the utilization of the path can have little variations that are creating disordering of packets. And so on the other side, on the destination leaf, you need to have a buffer to reorder the packets. And in general, it's very costly buffer. So the challenge here is to have the load balancing that is minimizing the buffer size at the destination node. And so to do that, you need the load balancing or congestion multipath congestion control algorithm that is making sure that you have no jitter or no as minimum as possible misordering of packets at the receiver side. In general, it's based on aggregated congestion information that is driving a global window evolution. So that's the current solution, so state-of-the-art solution. But at the moment, there is no consensus. There is no clear winner on a good load balancing algorithm. So it's a hot topic. And if you have bad load balancing, so you will have small congestions and the window will decrease, so we'll have poor throughput. And in some topologies where you have asymmetries or different latency, but it's really difficult to have good load balancing. At the same time, the topologies are also expanding. So you could have now in clusters, you could have regions that are where nodes are very close and you have ultra low latency where you can implement packet spray, but that are interconnected by a spine layer with higher buffers, higher delay, longer distance. So it means that if you want to do GPU to end-to-end communication between GPUs, you may need to switch between packet spray, flow-based, etc. So you may need a mix in the end, even if you see buildings. So it's a distributed data center, but within a quite local region. So that's load balancing. You saw the flow-based, the packet-based. So let's move up a little bit in the stack and come back to this collective communication layer. I show you the ring and the dual tree algorithm, double tree algorithm. Those algorithms, they were designed at the times where the topologies were super homogeneous and delay was bounded, there was infinite capacity, etc. Now it's not anymore the case. You saw in one data center, you have 3, 4, 5 types of technology, networking technologies, and the topologies is not a fat tree, much more complicated than a fat tree. I didn't mention, but inside the node, you also have PCI Express, which is also Ethernet-based. It's a network inside the computer. So when you assemble all this topology, you have something that is very heterogeneous in the nature, so in the technologies, but also in the utilization. So the workload is not uniformly distributed, and you don't have small flows that you can well balance, etc. So one topic is to have collective algorithms that are tuned to your particular topology. So we are talking about topology-aware algorithms so that you can take as input. So here's one example of paper from Microsoft called Topology-Aware Collective Communications, where as input you have the topology, a profiling of the performance of the topology. So you are characterizing the latency and the bandwidth that you have on each link. People are talking about the alpha beta model for latency and bandwidth. And based on this, you can synthesize, calculate, you can solve a multi-commodity flow problem or combinatorial problem to decide the scheduling for the transfer of the chunks and the routing of the chunks. So transfer times and routing times. So it's one topic, it's collective synthesization. The other one is that the collective you saw when you start exchanging chunks, as it can be an elephant flows, you don't want elephant flows in the network. So you could, at the source, in the SmartNIC side, you can already try to learn about the network so that you can split the flows in many and a good number for the network. So that is what I call collective adaptation, where you can see Q pairs. So Q pairs is the buffers that you have at the sender and the receiver in RDMA or in the Ultra Ethernet. And either you have one, so you can have only one buffer at the sender, or you can split. And for every Q pair, you will have a transport process. So it's a way to split a big flow into subflows so that later it is easier to load balance inside the network. So let's continue with another topic, which is the distributed data center. So distributing the training across regions. So that's there is interesting paper here that I invite you to read, which is I've got 99 problems, but flops aren't one. So you can buy GPUs. Okay, it's expensive. There is scarcity, etc. But the biggest part of the problem is on the interconnection of this compute. And so you need to have a new wide area transport for inter-DC, multipass transport, etc. And so a nice paper from Zurich ETH was to say, okay, let's let's try and do some distributed training over multiple data centers. And let's see if it has, if the fact that you have a bottleneck in the middle and the heterogeneous topology has impact on the completion time of collectives. And they show here that you have, for data parallelism in particular, so for all reduce, but you see that the performance are decreasing. So in various configurations, and they have unfavorable conditions as they go. The performance is really going down. But if the collective layer would have been aware of this one links or heterogeneity in the topology, you would have been able to get better topology. So the key message here is that for the scale across, you have things to do at the collective layer, but also at the transport layer. So that's this slide. So the transport layer, I told you about ECN and RTT, and in general, the buffers are very small inside the data center, so you have to rely on early congestion signals, so ECN. But if you go DC to DC, you have a much more delay plus large buffers in the middle. So you have to go RTT based. So one of the challenges is to design a transport layer algorithm, so a congestion control algorithms for the transport layer that is at the same time efficient for the inter-DC, but also performs still well in coexistence of traffic within the data center. So you have fairness issues between intra-DC traffic and the inter-DC. And why do we want to have multiple DC? So there's one slide on the power consumption you can see. And so if you have, depending on the model of the GPU you're using, the consumption is not the same. And so if you want to have a 100K cluster based on the latest version of GPU, it's several megawatts that you need. So that's well, there is not enough power locally, and so even in a region a few kilometers away, you have companies that are deploying DCs so that they can connect them to different sources of electricity. I think the last or the one before the last topic is on reconfigurable data center. So this one was there is a seminal paper from Google, which is a little bit old now, but it's a subject topic that is coming back. So inside the data center, you could use optical technologies on the spine switch with reconfigurable MEMS components, which are small mirrors that you can turn to modify the topology in the system. So you can create links here by moving mirrors. And so in this context, if you learn about the nature of the traffic, the workload that you have to accommodate, you can calculate the best topology to accommodate it. And so there is a paper called TopoOpt here. So Stefan Schmidt in particular has worked a lot on that. It's one of these papers on co-optimization between workload and the topology, or the optimization of the topology for a particular workload. So you can see here it's a two-stage optimization problem where you first parallelize your computation. Based on this, you know the traffic that will be sent. Once you know the traffic demand, you can optimize the data center topology. Now that you know the topology, you can re-optimize the parallelization strategy. And then you can iterate a few times until you converge to a good solution. And so the problem can be that you have given a routing model and you have a topology that you can change. You can calculate it, and you can do it with the different setups. So you can try to be oblivious. So you can calculate the topology that will accommodate a set of scenarios or most of the traffic scenarios, or you can be dynamic. So based on the demand, you can optimize it. But those MEMS, they are not, it's not it's not short period of time, so it takes some time to configure. So it's something that you can do, but at a slow pace. Um, I don't have a slide here, but one of the on the topology of data center and the optical part, I don't know if people are working on optical here. One on the hot topic at the moment is that the let's say the lambda is not anymore the currency, it's the fiber. So the people are developing optical switches that are switching fibers, entire fibers. So the demand is so huge that in between two DC, you have hundreds of fibers. And so it's no new granularity. And so that, I'm not expert in that, but you have hardware issues or hardware related topic. So as to design efficient devices. Maybe Ludovic knows from the old times. And the yeah, final one is I told you about the convergence between scale up and scale out. So if you look at one node, one GPU, so you will have a NVLink interface for the communication between with the other GPUs that are on the same machine or in the same rack, but another NIC to leave the rack. And so that is creating quite a lot of complexity. And especially for the people training the model, they don't really want to know if it's NVLink or something else. And so people are creating abstraction layers like fuse in for storage so that you hide this complexity. So that's I just to mention if some people are interested those two papers. So yeah, conclusion slide is the just I hope I convey the message that there are topics on the networking and there are topics. One challenge in this type of environment is that everything is evolving at the same time. So you have the GPU design is evolving, the machine learning frameworks and the way to parallelize computation is evolving, collective hardware transport topology, etc. So it's quite a huge topic. But at the same time, there are also proper abstractions. And in particular, for the networking layer, the collective abstraction and the primitives is kind of well separating the compute side from the networking side. So yeah, just to conclude, so you saw the two parts, some background about the technologies, another research topics, and some open questions. So can we converge to a good load balancing and transport? So I told you there is no consensus at the moment. There is a lot of secret sauce in all vendor solution or even the GAFA who are training their own model. They are touching the networking stack, so as to improve a bit the performance. Can we find a better way to cooperate between the network and the collectives? Can we unify the scale up and scale out? And what is the role of optical networking? I didn't touch too much this part, but just that the new currency is the fibers. Just if you are a PhD student, I don't know how many of you are PhD students, so how can I start in this mess? Um, and so that's my last slide here. So you have simulation tools, and in particular, one suite developed by Alibaba, which I think is quite interesting. It's grounded into one NS3 branch here that has implemented all the congestion transport mechanisms for congestion control. And then they expanded it in several papers with the collective communication layer and even a AI workload generator. So you can take a model, Llama 3, and then parallelize it over a certain infrastructure. So you will have a set of chunks that will have to be transmitted at different times, and then a collective layer that will schedule their transfers, and the transport layer that will really transport them from one GPU to another one. So it's a good starting point. So that's, yeah, so that's, I think, conclude my talk. Let me know if you have questions. Emmanuel is not here.
Hi. Okay. Thank you for the presentation. In the good old days of HPC, whenever there were more than 500 nodes and the computation took more than 1 hour, there were at least one fault.
Yeah.
You haven't talked at all about fault tolerance.
I didn't talk about it, but it's a good point. So there is a nice paper from Meta. It's a Silicon paper where they reported about the Llama 3, I think, trained over 20K GPUs, and they were reporting one GPU failure per day. And the training was lasting 2 months. So you have to live with indeed hardware failures. And so one way to deal with that, they do checkpointing. And so they are saving intermediate stages or the states of the models so that they can resume the training. At the time, this paper, everything was manual. You have an engineering team that is monitoring the execution of the training and then restarting the pieces of the training that had failed so that the training can continue. So at the workload side, one topic is to automate this part, clearly. And from the networking side, the challenge is what can you do if you have a GPU failure? Can the networking layer help? And that it's a difficult thing because if you lost data in a GPU, how can the network layer recover the data? So unless you have some redundancy, you have spread a little bit the data around. So that's one, I don't have the answer to that point. But yeah, indeed, it's reliability, fault tolerance is an important topic.
So yeah, so the scheme you describe is like what was used 20 years ago in HPC, so nothing very new. But there is also the problem of silent failures that you don't see it has crashed or anything, but somewhere in some memory chip, some bits were flipped. And there is no study about how this very small poisoning, random poisoning, is handled when you have to build a model with 100K GPU.
It could be. I didn't see things like computing hashes or verifying that the data are correct. But I didn't look particularly at this topic. There might be. Yeah.
Okay, thank you.
At the same time, just maybe to rebound, you see for this, people are also doing quantization. And here you have a loss, you have with lossy compression. And in this type of model, they could be also quite tolerant to losses.
Yeah,
So,
depends where the bit flip occur.
Yeah.
If
Yeah.
it's at the beginning of the number, then you quantize something.
Yeah, random quantization.
My question is a little bit in this sort of line. Is anyone considering like dropping determinism in computation and networking to support this sort of huge kind of architectures, which are probably not very picky about data itself because there's so much of it?
Yeah.
I was wondering,
It's a good question because I worked on a .NET, deterministic networking, like and people in the team also have a remaining work on .NET. We were wondering what could we do, and so you have to keep the GPUs busy. And so the principle is that okay, you have to reduce completion time, you have to reduce transfer time. So latency matters, and short latency, short completion times matters. But then whether you have to guarantee that you transfer things at a particular deadline, or That could be, but I didn't find yet the proper use case or the proper setup. So it could be that maybe you have a memory, you don't have enough memory at the receiver side, so the memory is shared between processes. So maybe but that part is the collective layer. So the scheduling of for the transfer of tensors. And that is articulated it's more the compute that is organizing the transfer and the computation. And then once it's decided, you have to be as fast as possible.
In this spirit, I mean, it would be like if something is not getting there, instead of orchestrating retransmission, etc., just dropping things on the floor and saying, well, I'm kind of lowering the confidence on the quality of this stuff, and then, well, it's going to be mashed and mangled together with so many other things, so that perhaps the exact transfer of data is not what matters any longer.
It all depends what is happening above, what is the operation, what do you do with the tensors? Maybe people are they are when you are aggregating gradients and so on. Sometimes you have distributed algorithms that could live with partial gradients, and so you could drop gradients. So you can do congestion control. If the transfer time is not enough, it could be that you just drop and you continue the calculation. The algorithm will be able to progress a little bit. So you have the challenge is to decide if you have enough information to run another iteration for the optimization part. But
I mean, since most of the projects are based on complexifying the network so that things can be guaranteed, perhaps there's an opposite way that, anyway, I will not monopolize.
Yeah, that's why the net is an overkill. And, maybe we don't need that. Unless we have a counter argumental use case, which I didn't find.
Thank you.
No. Thank you for an excellent talk, though it was quite complicated for me because I'm not at all from this field. But it is, I have still two questions which are a bit naive. Sorry for that. First question is, you mentioned energy consumption only towards the end of the talk for distributing processing at different sites or something like that. Does that mean that all these algorithms like the ring algorithm and all were designed to optimize performance? That means just speed, processing speed, and there was no consideration for energy consumption at that time?
No. Energy is not, unfortunately, energy is not a priority.
Okay.
It's the question is it's not only in general, even for a telecom operator, is what is the contribution in terms of energy consumption of the networking layer? Because you have many energy is sometimes consumed by optical transceivers or modules that you cannot really adapt. So there are parts in the elements in the systems that needs to be powered that are consuming already a lot. And so you are playing in the marginal. So in terms of gains, if you play with the network, maybe you will have up to 5% or I don't know. So and the question is it worth investing into network layer mechanisms that are energy efficient? And people have not looked at that.
So the second question is, NVIDIA, they make GPUs. I guess they make cabinets for data centers or whatever. And then Nokia, they make optical links, which are between different parts of the data center and between different data centers and all that.
So actually, yeah.
And so the question, this lack of, it's sorry for the ignorance. Who is the system integrator in this case?
Mm-hmm.
Who would deploy all these things you have
Yeah.
been designing?
So you have what I would call the full stack vendors. Like NVIDIA is actually a full stack vendor. So you have, they not only provide the GPU, but they also have all the networking with the Spectrum switches and so on. So they can build entirely, and Huawei is one. And then you have other vendors that are not full stack. So Nokia is not a full stack vendor. We don't have the compute. NVIDIA and Huawei, they have their own machine learning libraries, they have their own cluster management, they have their own networking, they have their own GPU, etc. And so for the others, indeed, you have to go through system integrators. So they are partners of Nokia that are system integrators and making the link between server providers, etc. At the moment, Nokia is on the network, on the optical part, on the IP routing part, so with data center switches and the routers for the interconnection of data centers. But for instance, we don't have smart NICs. We don't have, so we have to partner with the other people. Yeah, so it's an ecosystem really, especially for which is so you have to establish partnership.
Thank you.
We have some questions from remote. Daniel and Manon. Qui prend la parole?
Vas-y, Emmanuel.
Okay, thanks. Thanks, Dimitri, for the talk. Jérémie, sorry, lapsus. My question is, I was seeking to find a uniform solution for a problem which is not uniform. I mean, in your assumptions, it seems that all the data are local, the access can be equal and equivalent for in time and so on. You didn't discuss the diversity of the model foundations and the way it's done to have the learning and in your previous companies. I remember a talk from Wentong which was explaining how to improve and the performances thanks to actions during the learning. And even if I push the limit to the federated learning, what would be the impact of all of that? You started to discuss a bit the distribution in time and space at the end of your talk, but for majority of the first slides, I was asking myself the question about this kind of uniform and do we adapt the problem to the solution because the GPU are parallel? That's something that is maybe behind the reasoning.
Yeah. So indeed, I think the why I did that is that we are not full stack. So that could be taking elements I answered before. So we have to we are working in the scope of the network layer, and we are doing network acceleration. So we are not touching the workload, and we could have customers that are defining themselves the workload. And the proper abstraction between workloads and the network is this collective. So that's why I started from the collective communication layer. So the tensors have been the operation between the tensors and the location of the tensors are decided by the people managing the workloads. And once you have this, what can you do? So that was the rationale why I scoped the presentation like this. But indeed, you can do things. There are many topics at the interplay between the network and the workload management. That it would. I had also to select a bit the topics.
Thanks.
Welcome.
Yeah, my question was on the same direction. In fact, because as we all know, AI is becoming more and more distributed. But more than this is the fact that we are going to have an AI that will be more and more built with components coming from different providers. So my question was not directly on the core of what you presented, but about the control plane, something that some people are calling the governance plane, which is the one that will decide about the tensor, as you mentioned before. So do you know what is the state of the art on this specific topic? So, for example, if you we are talking about agentic AI,
Yeah.
and you will have agents broadly distributed, and you need to decide about the tensor, but dynamically, depending on the services you want to build. And more than this, you need to take into account also the access control logic of one AI to other AI and things of that sort. So we need a new kind of control plane on top of what you described. So is
So
there a chance to work on that?
I can answer with the agentic part because I'm hands-on on the agent stuff. So on the MCP, A2A, and the agent protocols. So agent is okay. It's defined by a prompt that is giving the instructions so that how it should behave, and then it can have access to tools and sources of data. But then on the back end, it's powered by an LLM. And this LLM can be remote. So it can be that you have multiple agents that are running on your enterprise network or inside your university. But actually, those agents, the intelligent part of this agent is totally offloaded with the processing of prompts that are contextualized by MCP. So all these agentic protocols so that the proper context is given and they can make decisions on how to use tools, plan the interaction between the different agents that they have at hand. But everything is kind of centralized. So the LLM can be executed locally, of course, but then in general, you don't have enough computation power, so you have to resort to small ones. If you want to leverage the bigger one, you have to go to a hyperscaler that is executing a GPT type of thing. So but here we are in the inference. We are in the inference part. So one topic is the creation of AI infrastructures that are used as backends for agentic systems and that are processing tokens. And so in this case, you have, I didn't cover it in the talk, but it's also a topic that we are looking at, is a control plane that is organizing the processing and the decoding of tokens between different computing nodes that are executing the LLM. So they can do the embedding of the prompt and they can do the decoding of subsequent tokens. So that here, it's really inference part inside the cluster as a backend of an agentic system.
Okay, thank you.
We have we have maybe one question at the back. We're already late.
Thank you. Thank you, sir. Actually, thank you for your presentation. It's really interesting for me. I'm currently a PhD student of Leguay Paris, and my topic is about observability of the network. And currently, I'm interested in the observability of a heterogeneous system. For example, when a CPU co-work with a GPU, it builds a very small heterogeneous system. Like we have some observed tools for CPU, like the flame graph, or of course we have something like an attack for the GPU.
Yeah.
I'm interested in how to combine these two together to build a more complete, a global observability framework. So my question for you is like, have you ever consider how to attribute or how to observe the performance issue or the bottleneck of when there is a lot of cross GPU execution, cross memory access, or the network transfer in such a uniform fabric? Or do you think the existing tools, profiling tools or observe tools, is sufficient, or do we need a more unified observability framework?
Okay.
Yeah.
I can just answer for the network part. So there is a lot of work done on telemetry so that the intermediate switches, they collect information about the traffic.
Yeah.
And also the SmartNIC side. So you could Before, well, there was not so much information, so there was a few indicators about the congestions, but now you can learn more about to have a good estimation of the latency or the buffer occupancy. And so that is the input data to a better load balancing, a better transport layer. Then after, for the compute part, it's honestly the monitoring of execution of GPU, a kernel in a GPU. It's not my topic, but I'm more focusing on the networking part.
Yeah, okay, just like you have talked about the KV cache, the KV value, like for when the CPU is when they are dealing with the KV value, maybe there is a lot of, I mean, idle, like CPU are waiting for the GPU or GPU are waiting for the CPU. So I'm interested in this kind of things.
In this pre-fill and decode part, you want to keep the GPU busy, and you also have multiple prompts to process in parallel, because you have an inference cluster that is serving many prompt requests.
Yeah.
And so I suppose the monitoring of the execution of this task is key to make scheduling decisions. So if you want to assign to a GPU decoding or a pre-filled task for inference, which will lead to production of the KV cache or the exploitation of the KV cache, then you need to have a very fine-grained monitoring of resource utilization. Otherwise, you will have waste, idle times, etc.
Yeah. Okay.
I'm sorry, there is another activity in the room. We have to leave the room, but I hope you'll join in room C06 now for a little moment of tea and sweets.
Okay, thanks a lot. But thanks for the invitation and thanks for the questions. Thank you.
Thanks a lot.
Merci.